Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 3. Applications of the derivative. Section 3.9. Related rates.
Lesson 1. Introduction and balloon example. Okay, today we're going to discuss a special kind of application problem which is called a related rates problem. And just as the title or the name of this type of application problem implies, these will be problems in which one rate of change is related to another rate of change. Okay, well, let me just preface this by saying that these are really cool application problems. They are very dynamic in nature, and they're kind of fun because they're going to use all of the calculus that you've learned so far. In particular, they're going to use the idea of implicit differentiation and the chain rule. And they are problems that you couldn't have possibly done a few weeks ago when you only knew algebra and trig. So they're cool because they're rather astonishingly dynamic problems, and you suddenly get to use all the tools that you've learned so far in calculus to be able to solve them. Okay, let's look at these remarks here. This first remark, I say, here we look at problems in which two quantities are related to each other. So one quantity is related to another, and each of those quantities is changing in time. Another way to say that is that each quantity is a function of time. So I'll put function of time. Okay, second remark. If we know the rate that one quantity is changing, so if we're given that rate of change, we can use calculus to find the rate that the other is changing. And that's the basic idea behind all of these problems. We'll try to describe how two quantities are related, and then given one of the rates of change, we'll try to use calculus to figure out what the other rate of change is. Okay, well, let's go ahead and look at a specific example, and you'll start to get a feel for what these problems are like. And let me preface all this by saying that we will use the same basic strategy and steps on all related rates problems. So if you can identify that what you are given is a related rate type of problem, you'll know the steps that you need to break the problem down and attack it one bit at a time. Okay, so let's look at this particular example so that you can understand sort of the generalities that I'm talking about in a more concrete kind of way. All right, so you're up in a hot air balloon when it springs a leak. So here you are down in the basket of the hot air balloon yelling help. You're looking up at the balloon. We're going to assume it's a perfect sphere. And here's the air coming out of your balloon. Yikes. You notice that the radius of the balloon is decreasing at the rate of 2 feet per hour. So you're looking up, and this perfectly spherical balloon has some radius r. And as you're looking up at it, you notice that that r is shrinking at this rate, 2 feet per hour. We want to answer the question, how fast is air escaping from your balloon? So how fast is this air coming out at the instant when the radius is 6 feet? So you look up and this radius is getting smaller, smaller, smaller. At some moment in time, it's exactly 6 feet. And at that instant, you want to answer the question, how fast is air coming out of your balloon? Well, each of these problems has its own challenge to it, but all related rates problems can be attacked and broken into parts by following the steps that we're going to look at. And there are 5 different steps, 2 of them on this page, and we'll look at the other 3 steps on the next page. So if it looks impossibly complicated, try to remember these steps. They're all quite important, and they will help you to attack and break up this problem into manageable pieces. First step, we're going to label the quantities that vary in time. And specifically, we want to look at the quantities that are discussed in the problem. So let's see if we can think about what quantities are changing in time, what quantities are functions of time. And one quantity that's going to be changing in time is the radius of the balloon, because as you look up, the radius is changing in time, and so it is a function of time. We may not know specifically what function of time it is, but we do know it's some function of time, and so I'm going to just write a general R of t, saying that R is a function of the input time. Well, what's the other quantity that's changing, that's described in this particular problem? The other thing is, notice it says how fast is air escaping from your balloon? How fast is air coming out of your balloon? And that has to do with the volume of the balloon, how much air is really measuring how much volume is in that balloon. So the other quantity that is changing in time is the volume of the balloon. And that should make sense. As the radius shrinks, the volume of this balloon is going to be changing. So the volume, that's really what it is thinking about when it's saying the amount of air. The volume is the other quantity that is changing in time. As time goes on, the volume of this balloon would supposedly be getting smaller. Okay, so that's step one, and it's quite an important step. Sometimes students want to skip that, but at least you need to think about it mentally, and I think it's a good idea just to write R of t and V of t. That way you've looked very specifically at what the quantities are that are related to each other. That's what we talked about in this remark number 1, and you've noticed that they are both functions of time. Okay, you remember that in this remark number 2 here, we said that if you know the rate one quantity is changing, you can find the rate the other is changing. And that's what step 2 in our 5-step process is all about. In each of the problems, there will be a rate that you know. In other words, a rate that is given to you. And there will be a rate that you want. In other words, a rate that you are asked to find. So when it says what rate do you want, is really what rate are you asked to find. So let's go through the problem, and here you may want to pause the video for a moment and try to answer this question yourself. What rate do you know? In other words, what rate of change is given in the problem? So think about that for 10 seconds. See if you can pick it out. Well, remember that a rate of change is going to be the rate that a quantity is changing in time. And which rate do they give us? They tell us right here the radius of the balloon is decreasing at, and here it says the rate specifically, of 2 feet per hour. And notice that feet per hour would be the correct units for the radius is measured in feet and time measured in units of hours. So the rate that we know is this 2 feet per hour. And I'm going to fix this up a little bit in terms of the sign in a moment, but before we do that, I want us to try to write this in symbols. It's a rate of change. It's the rate that this function R of t is changing in time. One way to write the rate that R is changing is to write R prime of t. Usually in related rates problems, though, we like to be very specific about what this derivative is being taken with respect to. So we usually don't use the R prime of t notation for the derivative, the rate that this function is changing. We usually use the dr dt notation. So it's the rate that R, the radius, is changing with respect to time. So it's the change in R compared to the change in t. So we would write that rate of change as dr dt. It's how fast the radius is changing in time. And I'm going to put a little equals here, even though there is a slight mistake in what I've written, and we'll talk about that in a moment. So you could write either R prime of t equals 2 feet per hour, although as I said there's a little mistake in there, or you could write dr dt, and in related rates problems we usually prefer this dr dt notation, so I'm going to stick with that. Well, I said there's a little mistake in here, and you may already have seen what that is. Remember that we said in this case, because of the way that the problem is described, that the radius, as time goes on, the radius is getting smaller. It's decreasing at the rate of 2 feet per hour. So if I were to draw a function that is decreasing in time, it would be a function that's going down as time goes on. Think about a tangent line at any point t, and what the slope of that tangent line would have to be. What would be true about the sine of the slope of this tangent line? A tangent line to a curve that's going down must be angled downwards, and so the slope of that tangent line must be something that is negative. So if r is a decreasing function, the slope of its tangent line is negative, and don't forget that r prime, same thing as dr dt, is graphically the same thing as the slope of the tangent line to the r versus t graph. So what is that saying? It's saying that dr dt has to be something that's negative. The radius is not increasing by a positive 2 feet per hour. We're losing radius. And so we're losing radius at the rate of 2 feet per hour. And we indicate that by saying that the rate of change of the radius with respect to time is a negative 2 feet per hour. We're losing 2 feet each hour. So I do need a negative sign in here. Okay, think about the second question. What rate do you want? In other words, what rate of change are you asked to find? So think about that for 10 seconds, and then we'll go ahead and look at it together. Okay, let's see if we can decide what we are asked to find. Notice it says how fast is air escaping from your balloon at the instant when the radius is 6 feet. So it says how fast is air escaping from the balloon. Well, how fast is air escaping from the balloon is really asking the rate. How fast is really asking for a rate that air is escaping. Remember, we said the amount of air is really measured by the volume of the balloon. So we are really asked to find the rate that the volume is changing in time. How fast are we losing air out of this balloon? How fast are we losing volume out of this balloon? Well, that's the rate that we're asked to find. Let's write it down in symbols. The thing I want to find is dv dt. If I can get my pen to write here, let me get a different green pen. I want to find dv dt. I want to find the instantaneous rate that the volume is changing with respect to time. How fast is v changing with respect to t? And notice that you're not asked to find it at all possible t values. You're really asked to find it at one moment in time, at the instant when you look up and the radius has gotten down to 6 feet. So the radius is shrinking, shrinking, shrinking. At some instant in time, it is 6 feet. I'm going to put this in sort of square brackets here. If I can get my pen to work, let's see if I can find, I'll just do it in red. I'm looking for the rate that the volume is changing at the instant when the radius is 6 feet. So I'm going to put that in parentheses because it's something we will use at the very end of the problem. I'll put at the instant when r is equal to 6 feet. And the reason we're going to put it in parentheses is that during the course of the problem, during the course of this situation that we're in, the radius is changing in time. It's a function of time. It's not a constant. If I were to use r equals 6 right at the beginning of the problem, I'd be declaring that the radius is constantly equal to 6 throughout time, 6 feet, and we know that that's not true. Let me see if I can write this in so that it is legible. So we want it at the instant when the radius is exactly 6 feet, and we'll use that information really at the very end of the problem. But we're going to write that in there to keep in mind that we want to know dv dt when, at the instant when r is equal to 6 feet. Okay, let's go ahead and go to the next page and see if we can talk about the other steps in solving this problem. So step 3, it says, what equation relates the quantities from step 1? And remember, the quantities in step 1 were the radius, which we wrote as a function of time, r of t, and the volume, which we wrote as also a function of time. Without thinking of them as functions of time, just think of the radius and the volume. And remember, these aren't the radius and volume of any old thing. They're the radius and the volume of this balloon, and we're assuming that the balloon is a perfect sphere. So they are really the radius and the volume of a sphere. So there's my radius r of my sphere. And is there an equation that relates the volume of a sphere to its radius? Sure. From geometry, you may not remember that formula. This isn't really a course in memorizing formulas, so you could always look it up. But the volume of a sphere from geometry is 4/3 times pi r cubed. So that's just a formula from geometry, and we're going to assume that either you remember it or, you Google it or something, geometry. So there is an equation that relates the radius of a sphere to its volume, and that is that equation. Now, I want to remind you that although I've just written v here, v itself is really some function of time. It's changing in time. So I'm going to replace this v here with v of t, since it's changing in time. The 4/3 pi is really a constant. And what about r? Remember that r is really a function of time as well. So I'm going to write r of t here. And whatever r is, I'm cubing it. So whatever r is at a particular time, I want to cube that expression. So I've just rewritten this relating equation here with the functions that are changing in time expressed clearly as functions of time. And that will help us in the next step. We have an equation here that relates v and r together. But that equation is not really relating what we are looking for. Remember what we are looking for. I'm just going to put the last page up for a moment. What we are looking for is dv dt. That's what we want. And the thing that we are given is dr dt. So we are not seeing that in this equation. I have a v of t and an r of t. I don't have anything relating dv dt and dr dt. So now we have this equation that relates v and r together. It's usually referred to as the relating equation, but it doesn't really involve the thing that I know or the thing that I want. If I put the last page on for just a moment, notice that the rate that I know is dr dt. That's the derivative of r of t. That's r prime of t. And the rate that I want, the thing that I'm looking for, is dv dt. That's really the derivative of the volume function, v of t. So the equation that I have is a nice equation that relates v and r together. Sorry about that, my pen is spreading for some reason. So this relates v and r together, but what I would really like is an equation that relates the derivative of v and the derivative of r together. I want something relating dv dt and dr dt together. Well, how do I get from this equation to something that involves the derivative of v and the derivative of r? I have to differentiate. So that's what we're going to do next, is differentiate this equation that we just wrote implicitly with respect to time on both sides. And why do I want to differentiate with respect to time? Because remember, we eventually want an equation that relates dv dt and dr dt together, not really an equation that relates v and r together. And these derivatives are derivatives with respect to time. So I'm going to go ahead and just rewrite the equation that I have up here. V of t is equal to I'm giving myself a little bit of room here. You'll see why in a moment. 4/3 pi r of t to the third power. And so we're going to differentiate this implicitly with respect to time on both sides. The idea is that if the left side equals the right side, then the derivative of the left should equal the derivative of the right if they're both derivatives taken with respect to the same variable time. So I'm taking the derivative with respect to time of the left side. That should equal the derivative with respect to time on the right side, or of the right side. Okay, so now let's go ahead and take derivatives. Well, I'm supposed to find the derivative of v of t with respect to time, but we don't know specifically what function of time v is. We just have v of t written here. It's some unknown function of time. Well, since we don't know what derivative it is, about the best we can do is just to go ahead and say, okay, that's v prime of t. And on the right side, let's start taking derivatives. Notice that I have 4/3 pi multiplying all of this stuff. So 4/3 pi is just a constant. And remember that a constant multiple can just be carried along. So the derivative of the right side will be 4/3 pi times whatever the derivative of this portion of it is. And 4/3 pi is a constant multiple, so that just gets carried along. Now I want you to think about taking the derivative of this expression with respect to the input variable time. Notice that I have r of t inside the cubing function. It's really got an inner function and an outer function. It's a composition of two functions. My inner function is r of t. It's what we thought of as g of x in our composition of two functions, f of g of x. So there's this inner function, and it's inside the cubing function. You could think of this as the t cubed function, where you write it with empty parentheses. But there's an inner function and an outer function. It's really a composition of two functions. And so what rule do I need to find the derivative of a composition? I need the chain rule. So in differentiating this, I will need the chain rule. Well, the chain rule isn't too hard to apply. Let's go ahead and do it. Remember, for the chain rule, we do derivative of the outer, evaluated at the inner, times derivative of the inner. So I start by taking the derivative of the cubing function, the outer function. And if I do that with empty parentheses, I'd be pulling down the 3, and all of this would now be to the second power. Chain rule says that I am supposed to do the derivative of the outer. That's what I've done, evaluated at the inner. Well, what's my inner function? It's this function r of t. So I'm going to just put r of t in there. So 3 times r of t squared, that's derivative of the outer, evaluated at the inner. But don't forget there's another factor in the chain rule. I have to multiply by derivative of the inner. Well, just like with v of t, we don't know specifically what function of time r is. So if I want the derivative of r of t, the best I can really do is write r prime of t. Okay. Well, this is fine. There's nothing wrong with this. I'm just going to clean it up a little bit. And instead of writing v prime of t, I'm going to just use our alternate notation because it's more traditional in these related rates problems. That's the main reason. And also, it's very specific in terms of we are taking the derivative of v with respect to t, that particular input variable. So instead of v prime of t, I'm just going to write dv dt. And let's see, over here, I could clean this up a little bit because it looks like the 3's drop out, so I would end up with 4 pi. And instead of r of t all to the second power, I put in the of t there just so that it would be clear that we need the chain rule when we take the derivative. That's why we went from r cubed to r of t cubed. So it was really for the purpose of doing this differentiation process that I rewrote this r that was right here as an r of t. Now to make things simpler, I'm going to suppress the of t and simply write this r of t as r. So instead of r of t, that quantity squared, I'm just going to say r squared. It's just simpler. And then the r prime of t I'm going to write in the alternate notation as dr dt. Notice that I went from an equation that related v and r together to an equation that related the thing that I want, dv dt, and the thing that I was given, dr dt. So by taking the derivative on both sides with respect to time, I transform my relating equation into an equation that relates rates together. And that's where the word related rates comes from. When we discuss this type of problem, you can see that the rate that the volume is changing is related by this equation to the rate that the radius is changing. Okay, let's go ahead and see if we can do the last step. Solve for the rate that you want. In other words, isolate the rate that you want. And actually in this case, if you remember the thing that we wanted, let me put the other page on for a moment, the rate that we wanted, dv dt, is actually already isolated on one side of the equation. If that weren't true, we would just go ahead and use algebra to solve for dv dt, to isolate it on one side. But in this case, dv dt is the rate that I wanted, and it's already all by itself on one side. So in this case, we don't have to do this step. But in some of the other examples that we see, we'll have a little bit of work to do to isolate the rate that we are asked to find. But this is the rate that I want from the last page. And then plug in all known values. And if you include their units, you can use that as a check to be sure that you've kind of done everything correctly. So I like to include the units as a check and make sure that I didn't make any errors. Well, dv dt is the thing that I want. So that I'm going to leave alone as what I'm looking for, an unknown. I have a 4 times pi times, and then I have an r squared. So let's see if we can figure out what value I should plug in for r. And then I have a dr dt, which was the rate that I knew. This was the rate that I know. And so if we go back to the last page, I just want to remind you that we knew dr dt. That was this value, -2 feet per hour. So I'm going to plug that in for dr dt. And the dv dt, we wanted not just at any general time, but at the moment in time when the radius is 6 feet. And that's where we're going to use this little information right here at the very end. Remember I said we're going to use that r equals 6 at the very end of the problem. R is changing over the course of our balloon springing this leak. But now at the end, we want to know what's dv dt at the moment when r is equal to 6 feet. And remember from the last page, we knew this rate, dr dt, was -2 feet per hour. So let me plug those things in. So I'm going to put in 6 feet for r. So that's plugging in for r. And dr dt was the rate that we were given. We were told that was -2 feet per hour. And I've included the units here, and I do that to make sure at the end that the units make sense, and it works as sort of a check that I've probably done the problem correctly. Well, let's multiply all of this out. I have 4 times 36 times -2, and I think I even plug that into a calculator. If we plug it all in, we get -288 pi for the number, 4 times 36 times -2. And in terms of the units, notice I have feet squared times feet. So that's going to be a total of feet cubed. And then I have a per hour here, so that's going to be a per hour. This would be the exact answer with the pi included. If you want an approximate answer, I just did 288 times pi on my calculator and got -904.8 cubic feet per hour. So that would be an approximate value. This is the exact answer to the problem. Now, before we leave this problem, I just want to be sure that it makes sense. Remember I said including the units can help as sort of a check. And the question becomes, are these the proper units for the rate that a volume would change in time? Remember that volume is in units of length cubed. So it makes sense that the volume would be measured in feet cubed or cubic feet. And then here's our unit of time. And so the units look correct. We're saying the volume is changing at the moment that the radius is 6 feet. That instant in time, the volume is changing at the rate of negative, or approximately negative 904.8 cubic feet per hour. So it makes sense that this would be a unit of volume per unit of time. So that looks good, and that gives us some confidence that we've done the problem correctly. It's just a check using the units. And what about this negative sign? Does that make sense? Remember that the volume of the balloon, would it be an increasing function or a decreasing function? If air is escaping from the balloon and the radius is shrinking, the volume must also be shrinking. And so it must be a function that's going down as time goes on. And just as we discussed with the radius function, which we said was a decreasing function, if I looked at the tangent line to a function that's going down, the slope of that tangent line, which is the same thing as dv dt, must be something that is negative in sign. And so it makes sense that this would be a negative 904.8 cubic feet per hour. What we're saying is that each hour, at that instant in time, we're losing volume at the rate of minus 904.8 cubic feet per hour. So we're losing 904.8 cubic feet per hour. Now technically I'll just mention that the way that the problem was originally stated, it said how fast is air escaping. This is how fast the volume of the balloon is changing. It's decreasing at that rate, and air is really escaping at the positive rate of 904.8 cubic feet. I should say approximately cubic feet per hour. So that's how fast air is escaping at that positive rate, and that's the amount of volume that the balloon is losing. So the negative is really the rate of change of the volume of the balloon, and the rate air is escaping would really be a positive 904.8 cubic feet per hour. So that's just a little side remark. That's just because of the way that the problem was asked. Okay, let's go ahead and look at another example.